All right, let's go to the next one. And I'm not going to focus too much on non-permissible values. Non-permissible values are very, very time consuming to get, and we can solve an equation. But determine the non-permissible values. I can get these by solving when we don't have a value. Now, consider that the numerator tan x. Tan x is equal to sine x over cosine x. So from the numerator, tan x, I get that cosine x can't be equal to 0. So that would yield pi over 2 plus k pi, where k is element of the reals. Now, if I take a look at the denominator, now my denominator is secant. Well, when is secant, by the way, can't be equal to 0, but secant is never 0. Further, secant is 1 over cosine of x. And really, what's hiding in the bottom is cosine x. So cosine x can't be equal to 0, but we already have that restriction. Last but not least, what's lurking in the denominator is we have sine x. So really, sine x cannot be equal to 0 as well. And really and truly, if you wanted to write the non-permissible values, there we are, right? Sine x is equal to 0 at these 2 points. Cosine x is equal to these 2 points. And maybe you're like, hey, my non-permissible values are x cannot be equal to k pi over 2, where k is element of the integers. That is just simply multiples of pi over 2. So now I'm going to simplify the above expression. Now notice this is an expression and not an equation. But in trigonometric identities, we treat each side of the equations independently, so we only work with expressions. So quickly in your head, tan x divided by secant x sine x is, I don't know. Let's see. So first things first, I'm going to write tan x over secant x sine x. And it's always a really good idea to try to break it down into its simplest elements, which are sine and cosine. So therefore, tan x is sine x over cosine x. Okay, getting a little squished. Maybe I'll write it over here. Tan x is sine x over cosine x. And secant x is 1 over cosine x. And then times sine x. I take a look at the numerator. Well, I need to think a bit. Before you go charging ahead, just think. Right? And if I look, wouldn't it be nice if I could get like the denominator to be like sine x over cos x? And in fact, 1 over cos x times sine x is sine x over cos x. So really, this just simplifies to 1. So tan x divided by secant x sine x is always going to be 1 for all x values, not including our non-permissible values. All right. Yuck. This next one. Now, this next one I can remember I really struggled with this next one. Verify the equation 1 plus tan squared theta minus secant squared theta is true for one angle. All right. So I guess what I'm going to do is I'm going to draw my unit circle here. What am I talking about? 135. 135 is that middle piece right there. Okay. Better keep this straight. So 1 plus, now tangent is probably tangent squared theta. I'm going to write it as tangent theta squared. I'm squaring my ratio. Is equal to secant squared theta. Now secant is simply just 1 over cosine theta squared. It's really incredibly important that you guys understand that I'm squaring the ratio, I'm not squaring the angle. There we are, we're back in action. So very simply, I have to prove that 1 plus tangent of 135 degrees squared is equal to 1 over the cosine of 135 degrees squared. I'm going to take my work up. 1 plus the tangent of 135 degrees is negative 1. So squared is equal to 1 over the cosine of 135. Well, the cosine of 135 is 1 over root 2, and I need to square that. So let me work on this a little bit. 1 plus negative 1 squared, so that'd be 1 plus 1. And the left-hand side is going to be, I'm going to square it. Actually, you know what? I'm going to multiply by the reciprocal of the denominator, and that would be root 2 squared. And what I get is root 2 is equal to root 2. Check. So this holds up. So I'm just going to write the above. Therefore, the above is true for theta is equal to 135. So have I proved it for all angles? No, it's not an identity yet. I haven't proved it. But anyways, let's move on. Recall. Recall that sine squared theta plus cosine squared theta is equal to 1. Demonstrate that 1 plus sine squared theta is equal to secant squared theta. I should write for all theta. Fair enough. How can I do that? So I'm just going to write sine squared theta plus cosine squared theta is equal to 1. And then I get a great idea. I ask myself, what is secant? Well, secant is really just 1 over cosine. What if I divide both sides of the equation by cosine squared theta? Well, then the right-hand side of the equation would be secant squared theta. Well, that's pretty good. But then the left-hand side of the equation would be sine squared theta over cos squared theta plus cos squared theta divided by cos squared theta is equal to 1 over cos squared theta. Yes, I got it. So now, sine squared theta divided by cosine squared theta is tan squared theta. Cosine squared theta divided by cosine squared theta is 1. 1 over cosine squared theta is secant squared theta. Therefore, tangent squared theta plus 1 is equal to, you know what, I'm asked to prove this. So I'm just going to restate my problem in terms of the original question. 1 plus tan squared theta is equal to secant squared theta for all theta. All right. Let's see if we can create a new identity, because we just created this identity just by messing around with the trigonometric ratios. So recall that sine squared theta plus cosine squared theta is equal to 1. Demonstrate cotangent squared plus 1 is equal to cosecant squared. To me, this is what gives it away. What is cosecant? Cosecant is 1 over sine. So if I divide both sides of this equation by sine squared theta, I am going to get sine squared theta divided by sine squared theta plus cosine squared theta over sine squared theta is equal to 1 over sine squared theta. 1 plus cosine over sine squared is going to be cotangent squared theta is equal to 1 over sine theta is cosecant squared theta. Therefore, cotangent squared theta plus 1 is equal to cosecant squared theta. All right. So I'm making up trigonometric identities here. If you notice, I'm messing around with both sides of the equation at once, and I'm dividing by the same quantities. Please don't do this. When you practice your homework, work with the left-hand side and the right-hand side. Because what essentially you're trying to do is you're trying to prove that the left-hand side is equal to the right-hand side. What I'm doing is I'm demonstrating that this sine squared theta plus cosine squared theta is equal to 1 can be written in an alternative way.